Hello everyone. Today we will going to study about physical and chemical equilibrium in detail. So let's start. Disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. So this is our index slides, and today we will going to study about all these topics majorly. So equilibrium state, concept of dynamic equilibrium, equilibria involving physical processes, Henry's law, general characteristic of equilibrium, equilibria involving chemical processes, types of chemical equilibrium, law of chemical equilibrium, equilibrium constants, characteristic of equilibrium constants, significance of Gibbs free energy in chemical equilibria, factors affecting equilibrium, Le-Chatelier's principle, and application of Le-Chatelier's principle. So let's start. Equilibrium state. Equilibrium is a general term which applies not only to chemical reactions but applies to physical changes as well. For example, ice and water are in equilibrium at 0 degrees Celsius and atmospheric pressure. So, uh, basically, ice and water is an example of physical change that it is are in equilibrium. They are in equilibrium at 0 degrees Celsius and atmospheric pressure. So, equilibrium applies to both chemical and physical changes. In a reversible reaction, the point at which there is no further change in concentration of reactants and products is called equilibrium state. So, equilibrium state is a name of a state at which there is no change in the concentration of reactants and products. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals number of molecules returning to the liquid from the vapor, right? Some important features of equilibrium state are: equilibrium is attained in a closed container, rate of forward reaction is equals to rate of backward reaction. At equilibrium, concentration of reactants and products becomes constant. So these are some points and these are some features of equilibrium state, right? So we have to keep these in our mind, and let's move on to the concept of dynamic equilibrium. Oh, sorry. Yeah. So the concept of dynamic equilibrium. Equilibrium is always dynamic in nature, that is, the reaction does not stop but goes on forward and backward directions with equal speed. In other words, we can say the equilibrium state is a dynamic balance between forward and backward reaction. So when the a balance is attained by the reaction between the forward and the backward reaction, that is known as the equilibrium is attained. So for example, solid is converting to liquid, so this is a physical equilibrium. For example, H2O in a solid state is converting to H2 in liquid at 273 Kelvin and 1 atmospheric pressure. So this is an example of equilibrium, physical equilibrium. And N2O4 in gaseous states going to 2NO2 molecule in gaseous states, and this is the example of chemical equilibria. Okay, chemically they are changing, their physical states remain same. Catalyst helps in attaining the state of equilibrium quickly without changing the position of equilibrium. Okay, so here we have talked about the catalyst that it helps in attaining state of equilibrium quickly without changing the position of equilibrium. So without changing the position, what will be the position of equilibrium, either forward, either backward? Catalyst just helps us in attaining the equilibrium quickly in a fast way. Okay. Equilibria involving physical process. So the characteristic of system at equilibrium are better understood by physical processes. This may be attained by the following ways. So, first, solid liquid equilibrium, like ice going to water. So, this is a solid liquid equilibrium. One status is one material or compound is in solid state, another is in liquid state, but they are interconverting at equilibrium. So, ice is equivalent to water. Rate of melting of ice is equivalent to rate of freezing of water. We can say this also, right? This is solid liquid equilibrium. Now, liquid gas equilibrium, water vapors, right? Like water to water vapors. So, rate of evaporation of water is equals to rate of condensation of water vapors. So, evaporation is equals to the condensation rate. So, third one is solid gas equilibrium. So, certain solids on heating directly change from solid into the vapor state without converting into the medium state, that is liquid state, right? And this process is also known as sublimation. So, like naphthalene in the solid state converting to naphthalene in the vapor state. So, this is happening at equilibrium state. Hence, this is an example of solid gas equilibrium. Okay. Let's move to the Henry's law. The equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. So there is a direct relationship between the mass of the solvent to the pressure of the gas, and it is given by Henry's law. So we can say that P is equals to KH mole fraction, where KH is the Henry's law constant and X you can say is mole fraction of gas in the solution. Okay, here O will come solution. No, here O will come so solution. Okay, so this is the Henry's law, and this is the equation or relation of Henry's law between pressure of gas and mole fraction of or mass of solvent. Okay, moving to the general characteristic of equilibrium. So, general characteristic of equilibrium involving a physical process are as follows. So, at equilibrium, all the measurable properties of the system remain constant, right? This is the first point. This is the first characteristic of equilibrium. Second, equilibrium is attained only in a closed system at a given temperature. So, this is a point to note that for a physical process or at equilibrium for a physical process, the equilibrium should be attained in a closed system. Okay. Third, equilibrium is dynamic in nature. That is, the opposing processes do not stop but take place simultaneously and with the same rate. So, equilibrium is dynamic in nature. Fourth characteristic, the physical equilibrium is characterized by constant value of one of its parameter, like melting point at a given temperature. So, the physical equilibrium, we characterize the physical equilibrium by a constant value of one of its parameter. Okay, like whether it's melting point, whether it's boiling point at a given temperature. Fifth characteristic, the magnitude of these parameters at any stage shows the extent of physical process up to which it has proceeded before reaching equilibrium. Okay, so the magnitude of the parameter like melting point, boiling point at any stage shows us the extent of physical process which is happening before reaching the equilibrium. Okay, this is the fifth characteristic. Okay, so equilibria involving chemical processes. The rate of reversible reactions at which the concentration of reactants and products do not change with time is known as chemical equilibrium. So, a reversible reaction rate at which the concentration of both side reactant and product do not change with time is known as chemical equilibrium. And there is a one term, active mass. We can define it as molar concentration and unit is mole per liter. So the example of the chemical equilibrium is H2 plus I2 giving us two molecules of HI, PCl5 giving us PCl3 plus Cl2, and this reaction or process is happening at equilibrium. So these are the example of chemical equilibrium. Yeah. Okay. Types of chemical equilibrium. So, on the basis of physical state of reactants and products, equilibrium may be of the following two types. So, on the basis of the physical state of reactant and product, we can divide it into two types: homogeneous equilibria and heterogeneous equilibria. So, homogeneous, in which reactants and products are in the same phase. So, the reactants and the product should be in the same phase for the homogeneous equilibrium. For example, there is process of production of ammonia, N2 plus 3H2 will give you 2NH3. You can see here that the reactants and the product are in same phase, are in same state, gaseous state, right? So it is an example of homogeneous equilibrium. Next is CH3COH, acetic acid in liquid state, plus C2H5OH, ethanol in liquid state, giving you CH3COOC2H5 plus H2. You can also see here that all the products and the reactants are in same phase, liquid state, right? So these are the examples of homogeneous equilibrium. Now, heterogeneous equilibria, in which reactants and products are in different phase. Yeah, like opposite of homogeneous, that reactants and products are in different phase. For example, calcium carbonate CaSO3 giving us CaO and CO2, and you can see that the reactant calcium carbonate in solid phase, the one of the product is in solid but other one is in gaseous. So it is an example of heterogeneous equilibrium. Another one, NH4HS in solid will give you NH3 in gaseous and H2S in gaseous. So the state in or the phase of reactants and products are different. So they are the example of heterogeneous equilibria. Okay, let's move to the law of chemical equilibrium. So what is the law of chemical equilibrium? At a given temperature, the product of concentrations of reaction products raised to the respective stoichiometric coefficient in balanced chemical equation divided by the product of concentration of reactants raised to their individual stoichiometric coefficient has a constant value. And this is known as law of chemical equilibrium. Okay, let's say this is a reaction. Okay, and A plus B, capital A plus capital B is the are the reactants, and capital C plus capital D are the products. And a small b are the stoichiometric coefficients of reactants, and small c and small d are the stoichiometric coefficients of products. And this reaction is happening at equilibrium. So this is equilibrium reaction. So the rate of forward reaction, you can write it as R subscript F, will be proportional to the concentration of the reactants like A and B to the power of their stoichiometric coefficient, small a and small b. So small a for the capital A reactant, small b for the capital B reactant. Okay, so we can introduce a constant here and remove the proportionality sign. So it will become RF is equals to KF A to the power A, B to the power B. Okay, where Kf is rate constant for forward reaction, because we are talking about the forward reaction here, right? Rf is rate of forward reaction. Now rate of backward reaction can be represented by Rb, is directly proportional to the concentration of products raised to the power of their stoichiometric coefficient, C and D. C for capital C and small d for capital D. And we can introduce a constant here too, that Rb is equals to Kb, C to the power C, D to the power D. So at equilibrium, Kf A to the power A, P to the power B is equals to Kb, C to the power C, D to the power D, because concentration become equal of reactants and products, right, at equilibrium. Now if we find the ratio, let name is it as K. So K is equals to Kf divided by Kb, so this will go here. So C to the power C, D to the power D, that is products, the concentration of multiple of concentration of products raised to the power of their respective coefficients divided by multiple of concentration of reactants raised to the power of their stoichiometric coefficients respectively, right? And here we have given that Kf is the rate constant for forward reaction, Kb is the rate constant for backward reaction. So the above expression is also known as law of chemical equilibrium. So this is the expression here. Okay, this is the important expression here, which we called as law of chemical equilibrium. And for a gaseous reaction, we can consider Kp is equals to pressure of C to the power C, means the to the power of their stoichiometric coefficient, dot Pd to the D power of D divided by Pa power A dot Pb power B, right? Where Kp is equilibrium constant in terms of partial pressure. So if we want to write out this rate constant or law of equilibrium, chemical equilibrium equation in the terms of partial pressure, we can write it in this manner or in this form. Okay, so Kp will be equal to the partial pressures of products divided by partial pressure of reactants raised to the power of their stoichiometric coefficient respectively. Okay, yeah. So let's move to equilibrium constants. So equilibrium constant like Kp and Kc and their significance. The ratio of concentration of products raised to the power of their stoichiometric coefficients to the concentration of reactants raised to the power of their stoichiometric coefficients at equilibrium state is called equilibrium constant. So when at equilibrium state, we are talking about the ratio of concentration of product to the concentration of reactant and the power of their stoichiometric coefficients respectively. We are stating this term as equilibrium constant, K, capital K. The equilibrium constant can be expressed in three ways. So first is equilibrium constant in terms of molar concentration, Kc. So we can write Kc is equals to the molar concentration of product divided by molar concentration of reactants and power to their stoichiometric coefficients respectively. Second is equilibrium constant in terms of partial pressure. This also we have seen. Kp is equals to the product of partial pressure of products divided by product of partial pressure of reactants. Third is equilibrium constant in terms of mole fraction, represented by K subscript X or mole fraction. So it will be equal to the product of mole fractions of products divided by product of mole fraction of reactants. Right? So these are the three equations, or these are the three manners by which we can write our rate of reactions in three terms, right? Let's move to more detail. So significance of equilibrium constants. If Kc, equilibrium constant, is greater than 10 to the power 3, what will happen? Products predominate over reactants. Okay. In other words, if Kc is very large, the reaction proceeds almost in all the way to completion. So reaction will follow the forward direction, right? If Kc is very large, the reaction will almost in all the way to proceed to the completion because it is a positive Kc, right? If Kc is negative or Kc is less than 10 to the power minus 3, reactants predominate over products. So reactant predominates over products here. In other words, we can say if Kc is very small, the reaction proceeds hardly at all. So it will not proceed in the forward direction. It will remain in the backward direction, right? And third, if Kc is in the range of 10 to the power minus 3 to 10 to the power 3. So if Kc is in the range of these two things, these two terms, appreciable concentration of both reactants and products are present. So because not the Kc is too small, not the Kc is too large, it is between these two range. So the concentration of both reactants products are appreciable, enough amount of concentration of reactants and products both are present. So these are the significance of equilibrium constants. Now, equilibrium constant helps in predicting the direction in which given reaction will proceed at any stage. For this purpose, we find out reaction quotient. So, equilibrium constant also helps us in predicting the direction in which our reaction will go on, in which our reaction will proceed at any stage. And for this, we also need our reaction quotient. So, reaction quotient is defined as ratio of molar concentration or reaction quotient partial pressure of product species to that of reactant species at any stage in the reaction. Okay, so we can represent the reaction quotient in both terms, like in molar concentration or the partial pressure, like in the reaction equilibrium constant, right? So the reaction quotient in molar concentration terms will be this, and reaction quotient in the partial pressure terms will be this. So these are the two equations for the reaction quotient. Now, at any stage of the reaction, if the reaction quotient is greater than rate constant, the reaction will proceed in the direction of reactants, or you can say reverse reaction. Okay, so if the quotient um, reaction quotient is greater than the equilibrium constant, then the reaction will proceed in the direction of reactants, or we can say that reverse reaction will happen. Second case is that if the reaction quotient is less than equilibrium constant, then the reaction will proceed in the direction of products, or forward reaction will follow. And third case is that they both become equal to each other, then the reaction mixture is already at equal. That means we are at equilibrium, not our reaction is not proceeding in any direction, but we are at equilibrium, right? Okay, so relationship between Kp, Kc and K in terms of mole fraction. So Kp is equals to Kc RT to the power del Ng. Kp is also equals to K mole fraction P to the power del Ng, where R is gas constant, T is temperature in Kelvin state, you del Ng is gaseous moles of products minus gaseous moles of reactants, and hence we can say that if del Ng is 0, del Ng become del Ng, if del Ng becomes 0, then Kp will become equal to Kc, because something to the power 0 is 1, right? So Kp will become equal to Kc, and no units for both Kc and Kp will be observable. Now, if del Ng will become positive, then this term will dominate. So Kp will become greater than Kc, and unit of Kc is mole liter inverse to the power del Ng, and Kp is atmosphere to the power del Ng. Now, if del Ng become negative, if this become negative, that means this right hand side will not dominate, right? So that means Kp will become less as compared to Kc. So unit of Kc is liter mole inverse del Ng, and Kp is atmosphere del Ng. Now, equilibrium constant in terms of activities, Ka we can say for the equilibrium constant. So Ka is equals to activity of C to the power C into activity of D to the power D divided by activity of A to the power A multiplied by activity of B to the power B, right? So this is also another manner or another type of equilibrium constant in terms of activity we can write. So activity is basically given by activity coefficient multiplied by the molality or molarity of the solution. So A is equals to gamma multiplied by M molality, or we can also write the molarity here and at the place of molality. So this is the activity relation. Okay. Now, characteristic of equilibrium constant. So, equilibrium constant Kp or Kc does not depend on pressure, volume, concentration, and catalyst, but it depends only upon temperature. For a given reaction, it is independent of reaction mechanism, It depends on stoichiometric coefficients, as you can see in the formula of equilibrium constant. For example, here is a reaction between H2 and I2 giving us 2 HI molecule, and the equilibrium constant here is Kc1 for this reaction. Now if we divide the reactants and the products by 2, so the reaction will become half of H2 plus half of I2 will give you HI2 divided by 2 will become 1. And let's suppose this reaction has equilibrium constant Kc2. So if we write the Kc2 in terms of Kc1, it will be Kc2 is equals to under root Kc1 or Kc1 to the power 1 by 2, right? So this is the relation we are defining, that if a reaction is given and we are doing some changes in it, so how their equilibrium constant will get affected, will get changed. So Kc2 will become equal to under root of Kc1. And if we reverse this reaction, so Hi will we reverse this reaction, not this, okay, because here also half is present. So if we reverse this second reaction, so Hi will give you half of H2 plus half of I2 molecules, and the equilibrium constant is Kc3. Now Kc3 will be equal to half 1 by Kc2, okay, because we are reversing it. So if the third equation has equilibrium constant Kc3 and we are writing it in terms of Kc2 because we reverse the reaction of second reaction which is having equilibrium constant of Kc2. So Kc3 will be equal to half 1 by Kc2, or Kc2 we have Kc2 is equals to under root Kc1, so we can also write Kc3 is equals to 1 by under root Kc1. Okay. If a reaction is multiplied by n, the rate constant Kc becomes Kc to the power n. N can be fractional also, but it is only positive value. Okay, we have seen here also this. If K1 be equilibrium constant for this reaction, P is going to Q, and K2 be equilibrium constant for this reaction, R is going to S. Now equilibrium constant for P plus R going to Q plus S is K1 into K2. So if we add two reactions, their equilibrium constant get multiplied. Okay, so so P going to Q has K1 equilibrium constant, R going to S has K2 equilibrium constant. Now we add these two reactions, so their equilibrium constant, the equilibrium constant for final reaction will become K1 times K2. For exothermic reactions, equilibrium constant decreases with the increase in the temperature. And for endothermic reaction, equilibrium constant increases with the increase in temperature. And for reactions having zero heat energy, temperature has no effect. Okay, these are some important points. Del G, significance of Gibbs free energy in the chemical equilibria. Del G for a reaction under any set of conditions is related to its value under standard conditions, that is del G naught by the equation del G equals to del G naught plus 2.303 RT log Q. So this is the relation between del G and the del G under standard condition, which is del G naught. Under equilibrium conditions, for same number of moles of reactants and products, the del G becomes 0 and Q will become equal to the rate constant in terms of partial pressure, in terms of concentration, or we can say as K. So del G naught on del G becomes 0, del G naught will become equal to minus 2.303 RT log K. Yeah. Significance of del G naught are given below. If del G naught is less than 0, log K will be greater than 1. That means K will be greater than 1. Therefore, forward reaction is spontaneous. Second case, if del G naught is greater than 0, so log K will become less than 1 and K will become less than 1. Therefore, backward reaction is spontaneous. Third case, if del G naught become equal to 0, now log K will become equal to 0 and K will become equal to 1. Therefore, reaction is at equilibrium. So these are three terms, or these are three conditions of del G naught, where we can decide what the uh, what will be the behavior, or the direction of our reaction will be, how it will react. Note relation between degree of dissociation and density degree of dissociation. Alpha of a gaseous compound is related to its vapor density by this equation. Alpha equals to capital D minus small d divided by small d multiplied by y minus 1. We can see that D is equals to molar density before dissociation, or initial density, we can say. Small d is density after dissociation, or density of the gaseous mixture, and Y is number of moles of products. And this is the relationship between these two things, degree of dissociation and density degree of dissociation. Okay. Now, density of gas, we can write it as molecular weight divided by 2, or molecular weight will be equal to density of gas multiplied by 2. So MO is equals to D into 2, or MC is equals to small d into 2. Here, MO is observed molecular weight, which is generally abnormal, and MC is calculated molecular weight, which is theoretical, we can say. Right? Now, the principles state that, okay, so factors affecting equilibrium. So we can also say that Le-Chatelier's principle. The principle states that change in any of the factors that determine the equilibrium condition of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. So at equilibrium, if some change is happening, this principle states that the equilibrium counteract that, if the effect of that change. So different factors affecting equilibrium are discussed below. First, effect of concentration change. The concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance. So if we at equilibrium, if we are adding the reactant or product, then this concentration change will be relieved by the net reaction in the direction that consume that added reactant or product. Okay, so reaction will shift itself in that particular direction. So let's suppose this is a reaction A plus B giving us C. So if we increase the concentration of either A or B, that is reactants, the equilibrium goes in the direction that consumes A or B, that is forward direction, right? If we increase the concentration of C or product, the equilibrium goes in the direction that consumes C, that is backward direction. So reaction will follow in the backward direction. If we remove C or product, the equilibrium goes in the direction in which its concentration increases, that is forward direction. And if any of the species is in solid or liquid state, its addition does not alter the original equilibrium. So these are some points. These are some points we have to keep in our mind when we are talking about the effect of concentration change. Here a point is written that sweet substances causes tooth decay because on fermentation these produce H positive ions which combines with OH minus ions and shift the equilibrium in forward direction. And this is the reaction process for this point or for this example. Right, so this is the reactant going in the forward direction, which is demineralization, and in the backward direction it is remineralization. So second effect is effect of pressure. So at high pressure, reaction goes from higher number of moles to lower number of moles, or from higher volume to lower volume, and vice versa. So if del Ng is 0, no effect on equilibrium due to pressure change. If del Ng is positive, the increase in pressure favors the backward reaction. And if del Ng is negative, the increase in pressure favors forward reaction. And del Ng we know is number of moles of gaseous products minus number of moles of gaseous reactants. Third is effect of temperature. So at high temperature, reaction goes to endothermic direction, while at low temperature, reaction goes to exothermic direction. The equilibrium constant for an endothermic reaction increases as the temperature increases. So K is directly proportional to temperature if del H is positive, that is endothermic reaction, and K is inversely related to temperature if del H is negative, that is exothermic reaction. So in the case of endothermic and exothermic, K is directly related to T in endothermic and K is inversely related to T in exothermic. Fourth is effect of catalyst. A catalyst increases the rate of forward reaction as well as rate of backward reaction. So it does not affect the equilibrium and equilibrium constant. So there is no relationship or no effect of catalyst on the equilibrium and equilibrium constant. Fifth, effect of inert gas. At constant volume, there is no effect of addition of inert gas. At constant pressure, when inert gas is added, reaction goes from lower number of moles to higher number of moles. So this is the effect of inert gas. Application of Le-Chatelier's principle. The Le-Chatelier's principle is applicable to physical as well as chemical equilibria. Some of its applications are mentioned below. First, to chemical equilibria. Haber's process of synthesis of ammonia, we can see N2 plus 3H2 will give you 2NH3 and del H is negative for this reaction. So, to get better yield of ammonia, required conditions are high pressure as del Ng is negative, low temperature as reaction is exothermic, high concentration of reactants and removal of NH3. And to the physical equilibrium, effect of pressure on melting point like ice water equilibrium, ice from solid going to water and liquid. An increase in pressure favors the melting of ice into water because the volume of ice is greater than volume of water. Therefore, on increasing pressure, more and more ice will melt. And the effect of pressure on solubility of gas. So let's suppose gas plus solvent will become a solution. So an increase in pressure always favors the dissolution of gas in the solvent. Therefore, the solubility of gas increases with the increase in pressure. And the amount of gas dissolved per unit volume of solvent is directly related to its pressure, and it is Henry's law. That is, M is directly proportional to P. So effect of temperature on solubility of solids is third. That is, if solute plus solvent will give you solution and del H is positive. An increase in temperature always favors endothermic reaction. Therefore, solutes having endothermic dissolution show an increase in their solubility, with temperature, and solutes having exothermic dissolution show a decrease in their solubility with temperature. So these are some factors which affect the chemical equilibrium according to the Le-Chatelier's principle. Okay, so we are at our summary slide. So the equilibrium state is a condition in a chemical or physical process where the rates of forward and reverse reactions are equal. Henry's law states that the amount of a gas that dissolves in a liquid at a given temperature is proportional to partial pressure of that gas above the liquid. The equilibrium constant K quantifies the position of equilibrium for a reversible reaction. It varies with temperature and provides insight into the extent of the reaction. Gibbs free energy del G indicates the spontaneity of a reaction, and at equilibrium del G is equals to 0. A negative del G favors the formation of products while a positive del G favors the reactants. So these are some major points which we have studied today. Okay, thank you.